All right, 2.1, we're going to talk about defining average and instantaneous rates of change. And our objective today, we're going to represent a derivative as a limit of difference, a limit of a difference quotient, rather. So we're jumping back to here. You might remember at the beginning of the year, we talked about how do we find a slope on a curve at a single point, meaning the slope of the tangent line to that point. And we kind of already talked about this. The slope of the tangent represents the instantaneous rate of change of that curve at that point. And the way we approached that was we found the slope between point P and various other points Q that get closer and closer to P. And so this blue line, PQ, is a secant line. And I want to be clear that the slope of these secant lines represents an average rate of change over that interval. All right, and the way we found that average rate of change was just your algebra 1 slope formula, right? y2 minus y1 over x2 minus x1. And then we introduced the idea of a limit, and a limit allows us to kind of look at behaviors as we get infinitely close to a certain point. And so what I can then do is let x approach a. So now I'm taking this limit, I'm going to let x approach a. A is a fixed point, and x is my variable point. And I'll move it infinitely closer to a, and we'll keep finding the slope of that secant line. And so now that instantaneous rate of change just becomes a limit. And in our arsenal, we've developed a bunch of ways to evaluate limits, right? All right, well, this is called a difference quotient. Right? You got your difference and you got your quotient. So the limit of the difference quotient as x approaches a gives you the slope of the line tangent to the fixed point. So in example 1, we're going to find the equation of the tangent line to the parabola y equals x squared at the point 1, 1. So I'm going to sketch out this situation for us first. Sometimes it's good to have a little bit of a geometric understanding about what's going on before we jump into the algebra of the situation. All right, so we have our parabola, that's y equals x squared. We have our fixed point, which is 1, 1. We're now going to apply our limit definition of difference quotient to find the slope at that point. So what we want, remember, is the slope of this line, the tangent line that goes through 1, 1. And the way we'll do that is take your function, you're going to subtract f of the fixed point over x minus the fixed point. Except now I'm going to change this into a limit. We're going to let x approach the x value of that fixed point. So this becomes f of x is just x squared. F of 1 would be 1 over x minus 1. All right, so now is when our sort of arsenal of different ways to evaluate a limit comes into hand. The first thing you might try is a direct substitution. So just plugging in 1 for the x's. But we quickly see if we do that, we get 1 minus 1 over 1 minus 1, which is 0 over 0. And when we're evaluating limits, that's just an indeterminate form. that does not necessarily mean that the limit does not exist. And so now we think back on all the stuff we learned. Well, can I simplify this? In fact, we can. We can factor the numerator, right? That's a difference of two squares, x minus 1 times x plus 1 over x minus 1. Then we notice, oh, we have a common factor of x minus 1. So I can look at the limit as x approaches 1 of x plus 1. And now I'm ready to try my direct substitution one more time. And I get 1 plus 1, which is 2. All right, great. So the slope of the tangent line at that point is 2. Now, pay attention to what the question is asking us. It wants the full-on equation of the tangent line, not just the slope. So now we're going to go back to using that point slope form. I can write it out like this. We do y minus the y coordinate, so y minus 1 equals the slope times x minus the x coordinate. There you go. And you can totally just leave your answer like this. I'm 100% fine with that. Some of you are maybe averse to that. Add the 1 to the other side. You can distribute the 2. We get y equals 2x minus 1. All right, let's take a look at this in GeoGebra. All right, so here's our parabola. Let's put the point 1, 1 on there. And then let's look at our answer. Y equals 2x minus 1. There you go. Slope of the tangent line at that point. One thing that I want you to notice is that I can zoom in as far as I like, and at some point you can't even tell the difference between the parabola and the tangent line when I get close enough. So that's a really important characteristic called local linearity. If you can zoom in to the point that your graph looks linear even when it's curved, your function has something called local linearity at that point. What that's going to end up meaning is that we're able to find a slope at that point. There are certain functions where at certain points they do not ever achieve local linearity no matter how much you zoom in. So if we look at, like, let me get zoomed out here. Let's look at something like the absolute value of x, but I'll shift it up, plus 2. So if I look at an absolute value function and I look at the point 2, 0, or sorry, 0, 2, that's where its vertex is. I can continue to zoom in on that point, and I will never achieve local linearity. It'll always just look like a sharp point. So that's in contrast to something that's a smooth curve and not a sharp point. If it's a smooth curve, you should be able to zoom in on it enough where you get that local linearity. All right, so we're going to come up with another expression that represents the difference quotient, but that's written a little differently. And this might look like it's more confusing, but it's actually generally easier to use. This definition is fine, but it becomes problematic because a lot of times the work you have to do, you have to be able to get rid of this x minus a in the denominator so that you don't end up with an indeterminate form. Now, as long as your numerator is something like this that factors very easily, that's not a huge issue. But a lot of times you don't get that nice of a numerator that factors out really easy. So we're going to take that difference quotient and write it in a different way. here's how we're going to do it. We're looking at the same setup. I still want to find the slope of my tangent line, okay, at point P. But I'm going to define things differently. Before, I just defined this as point X. What we're going to do is define this now in terms of the width of the gap. So this gap, the horizontal gap between A and this point Q that we're moving infinitely close to point P, that horizontal gap we're going to call H. So that if this is A, then this coordinate is A plus H. Okay? And then we're going to apply our definition of slope using this new set of coordinates. So you can see Q has variable coordinates A plus H and then F of whatever A plus H is. So applying that same slope formula, M equals F of A plus H minus F of A over, then I do A plus H minus A. Same exact idea as what we were doing over here. We're just defining our points a little differently. Instead of calling this X, we defined the gap, right? All right, so, but it's finding the same thing. So now the limit, when I want my point Q to approach my point P, what I want to do is close this gap down. So I want that gap, that H, to approach 0. And what you'll notice is that in the denominator, you have A and negative A. Those cancel out. And that's just going to leave me with the limit as H approaches 0 of F of A plus H minus F of A over H. And so instead of having a binomial in the denominator that we had to get rid of, we now only have an H. We have a monomial, a single term in the denominator, which is usually a little easier to get rid of. You don't need things to factor out as nicely. But remember that these are both finding the same thing, which is the slope of the tangent line at the point P. So let's do this one. We're going to use the new definition. Find the tangent line to the hyperbola y equals 3 over x at the point 3, 1. Now you may not off the top of your head know what 3 over x looks like as a graph, but I'll show you just because I think, again, understanding the geometry is a little bit easier. Or maybe you do know. It's just going to be something like this. Keep your eye on the prize. What we're looking to do, they're saying that's the fixed point 3, 1. We want to find the slope of the line tangent at that point. Oh, I'm sorry, find the equation of the tangent line at that point. So remember that the A is your fixed x coordinate. So this is our A. Our A is 3. And we're going to use our new definition, which was this one, right? The slope equals the limit as h approaches 0 of f of, now in this case, 3 plus h minus f of 3 over h. Okay. Let's continue. The limit as h approaches 0. F of 3 plus h, you're just replacing the input, the x, with 3 plus h. So I'm going to get 3 over 3 plus h minus f of 3, we're told is 1. So minus 1 over h. All right, let's say we tried to evaluate this limit by substitution right off the bat. We would plug in the 0 for h. We would have 3 over 3 minus 1 over 0. That comes out to 0 over 0, which is our indeterminate form. Again, does not necessarily mean the limit doesn't exist. It means we need to do some tricks, some algebra to try and simplify the limit and then resubstitute. All right, you guys have done problems like this in your homeworks in the past. So anytime you have a complex fraction, you'd like to make it non-complex. So I'm going to rewrite my 1 as 3 plus h over 3 plus h, so I have a common denominator there. That's going to give me 3 minus the quantity 3 plus h. That's over the common denominator of 3 plus h, all over h. You can go ahead and put your h over 1 just so you have a fraction over a fraction, and that'll be a little clearer what to do from there. You flip the bottom one and multiply. So I'm going to have 3 minus the quantity 3 plus h over 3, oh, that was bad, 3 plus h times 1 over h. All right, so let's simplify. Really key to making sure that you put this 3 plus h in parentheses so that you remember you have to distribute the negative to both those terms. Now I'm at limit as h approaches 0, 3 minus h over the quantity 3 plus h times h. Notice that the 3's cancel each other out. I'm just left with negative h. Now, since I also have an h in the denominator, I can divide those out. Now we're left with the limit as h approaches 0 of negative 1 over 3 plus h. Now we can do our direct substitution. Negative 1 over 3 plus 0, negative 1/3. Whoops, sorry, I'm writing in my picture area. All right, that is my slope. Again, pay attention to the original equation. We want the equation of the tangent line. And again, you can just leave that equation in point slope form. So I'm going to do y minus the y coordinate, which is 1, equals my slope, times x minus the x coordinate, which is 3, and that's it. That's the equation of my tangent line. Let's go ahead and check that once again in GeoGebra to make sure that it looks like it's the correct answer. Oh, I zoomed way in. Let me just get a new, there we go. All right, so our function is 3 over x. The point that we want the tangent line at was 3, 1. The equation we had was y minus 1 equals negative 1/3 times x minus 3. Boom. Tangent at that point. Let's check out the local linearity there. I'm zooming in. You can see that they're getting closer together. And then I can achieve local linearity at that point for my y equals 3 over x graph. All right, another example. Suppose a ball is dropped from the upper observation deck of the CN tower 450 meters above the ground. What is the velocity of the ball after 5 seconds? So here is your position versus time function. So plugging in time t will get you the ball's position. This is just a parabola. And really, we only care about the right-hand side of this parabola because we're looking at position versus time. We only care about time starting after time 0. So say that this is 5. If we found the slope between time 0 and time 5, it would be the slope of this line. Slope is rise over run, which would be units of meters over seconds. So it's going to give us a velocity of some kind. Now, remember what we said. The slope of a secant line is an average rate of change. The slope of a tangent line is an instantaneous rate of change. So if I were to do f of 5 minus f of 0 over 5 minus 0, well, you can plug in 5 to 4.9t squared, you're going to get 122.5. Plug in 0, you'll get 0 over 5. So let's see, 122.5 divided by 5 is 24.5. And that's meters per second. But this is not what they're asking for, because this is the average velocity over the first 5 seconds. So from time 0 to time 5. What we would like is the instantaneous velocity. We want the slope of that tangent line at time 5. All right. And so to find that, we're going to use our limit as h approaches 0. And remember that the x value of your fixed point is a. So I'm going to have f of 5 plus h minus f of 5 over h. All right, let's see. Limit as h approaches 0. In this case, I'm just going to replace the input on my function with 5 plus h. So the input is t. This becomes 4.9 times 5 plus h squared. We already said f of 5 was 122.5 over h. So again, if you try and plug in the direct substitution at this point, you probably guessed this, you end up with that indeterminate form. So what you need to do is expand out your numerator, and hopefully you'll be able to get rid of the h in the denominator at some point, right? So let's see, limit h approaches 0, 4.9 times 25 plus 10h plus h squared. Remember, you cannot just square the h and square the 5. That does not follow order of operations. You have to multiply 5 plus h by itself and FOIL that out. Minus 122.5. Okey-doke. Distribute the 4.9. Oh, whoops, this is all over h. Distribute the 4.9. You end up with 122.5 plus 49h plus h squared minus 122.5 over h. Those 122.5s cancel each other out. Notice that all the terms that are left in the numerator have an h in them, so I can divide out an h. It's going to give me the limit as h goes to 0 of 49 plus h. Now I'm ready for that direct substitution, and I end up with 49 meters per second. So the speed, the instantaneous speed at time 5 seconds is 49 meters per second. Remember, we did this problem at the beginning of the year, but where we made a table in our calculator to estimate the slope. You can kind of go back and look at the notes and see that we did guess about 49 meters per second. All right, how fast is the ball traveling when it hits the ground? So the first thing we need to know is when it hits the ground. And it hits the ground when its position is at 450 meters, because that's how tall the tower is. So what we need to do is set the position function (4.9 t squared) equal to 450. We're going to need to solve. So I'll divide out the 4.9 take the square root. Oops, not 4.5, 4.9. Let's get an approximation here. All right, so I get about 22.361 seconds. So if we're going to do this, we need to do the same thing again with 22.361 seconds. So let's do that. Oops. So now our A is going to be 22.361. So I'm going to say the slope, which is the instantaneous velocity, the tangent line, whoops, it's going to be plus h minus f of 22.361 over h. All right, 4.9 times 22.361 squared is 2450.070. All right, so once again, you need to multiply out the numerator. And I will tell you that 22.361 squared times 49 equals this. So 2450.070. Oh, sorry, I'm getting a little bit ahead of myself. 4.9 times 22.361 squared plus 44.722 h plus h squared. .070. All right, and that's all over h. All right, so now when we distribute the 4.9 to everything, 4.9 times 22.361 squared is exactly this 2450.070. Those terms are going to cancel each other out. So then I'm left with 4.9 times that number. So 4.9 times 44.722. All right, and that's my 219.138 h plus 4.9 h squared all over h. And again, I'm able to divide out an h since each term left in the numerator has one. Now I'm going to make my direct substitution of 0 in for the remaining h, and it's just going to leave me with that 219.138. So because I rounded, I'll say approximately 219.138 meters per second. Oh, sorry. Okay, well, what we've been doing is finding derivatives. The definition of the derivative the derivative of a function f at a number a, and we'll denote that f prime at a. So this little guy, the little tick, that's called prime notation, is the limit as h approaches 0 of f of a plus h minus f of a over h. Or this is also a definition of derivative. Remember that that was just an equivalent way of finding a slope at a point. That's all a derivative is. It's an instantaneous rate of change, aka the slope of a tangent to a point. Okay, so find the derivative of the function f of x equals x squared minus 8x plus 9 at the number a. So they're going to have us abstract this idea. I'm going to go the limit. So we'll use our prime notation. F prime at a equals the limit as h approaches 0 of f of a plus h minus f of a over h. All right, so the first part of our numerator, we're going to replace all the x's with a plus h. That's going to give me a plus h squared minus 8 times a plus h plus 9 minus f of a. So now I'm just replacing all the x's with a's. So a squared minus 8a plus 9 all over h. All right, let's expand out our numerator as much as possible. So now I have the limit as h goes to 0 of, that's going to be a squared plus 2ah plus h squared. If I distribute the negative 8, I get minus 8a minus 8h plus 9. Distribute this negative to all three terms. It's going to give me minus a squared plus 8a minus 9 all over h. All right, let's combine any like terms that we have. A squared, I have a negative a squared. Those cancel. 2ah, I don't have any other ah terms. H squared, I don't have any other h squared terms. I have negative 8a and positive 8a. 8h, I don't have any other h terms, and I have positive 9 and negative 9. Those cancel out. So I'm left with the limit as h goes to 0 of 2ah plus h squared minus 8h all over h. Well, once again, all the terms left over in the numerator have at least one factor of h in them, so I can divide out that h. Limit h approaches 0 of 2a plus h minus 8. Now we're ready to do my direct substitution, and we're left with 2a minus 8. So what does this tell us? Our derivative at any point a is 2a minus 8. Well, a, remember, is the x-coordinate of the fixed point that you are trying to find the derivative at, that you're trying to find the slope at. So this is basically a formula for the slope of this parabola at any point. All you have to do is plug in its x value a, and this will spit out the slope of that parabola at point A. All right. So now we've been finding equations of tangent lines. We can kind of generalize our results. The tangent line to the function y equals f of x at some point a f of a is just the line that goes through a f of a, whose slope is equal to f prime at a, the derivative at a, which is also called the instantaneous rate of change. So this parabola, if I want the slope at the point 3, negative 6, we just found out, this was the same parabola we were just working with. We just found out that f prime at a is just 2a minus 8. And so if I want to find the slope at the point 3, negative 6, I'll just plug in the 3. A is the fixed x-coordinate. All right, well, the slope should be negative 2. So then the equation of the parabola is y minus the y-coordinate equals the slope times x minus the x-coordinate. Just clean it up a little bit. That's y plus 6 equals negative 2 times x minus 3. And that's my claim. That's the slope of the line tangent to the point 3, negative 6 for that parabola. Let's just take a look at GeoGebra one time. A bit zoomed in there, so let me get zoomed back out. Put myself over here. All right, our parabola is y equals x squared minus 8x plus 9. We want to know what's going on at the point 3, negative 6. We said the equation of the tangent line is going to be y plus 6 equals negative 2, times x minus 3. There you go. Perfect tangent line. All right, we're into proper calculus now. Finding derivatives. Here's your student example. Go ahead and pause it here. Try and come up with the answer, and we will discuss in the next class. All right, have a good one, folks.